Hello guys, still stuck with using batteries as a method of storing energy? Well, not anymore, because the future of energy storage is here. So hop on and tighten your seatbelt, because you will be driving the future with us. Team 2 from CS350 presents to you Kappa Cards, a futuristic innovation in efficient energy storage. We will be covering the following in our presentation: system overview, system architecture, class diagrams, user interface, use case diagrams, and lastly, sequence diagrams. So let's get started with system overview. As stated before, our Kappa card system uses supercapacitors for storing energy instead of batteries because supercapacitors are faster at storing energy and also can store a lot of energy compared to batteries. The system also allows the user to see real-time SOC and temperature values of the supercapacitor and also allows the user to change the drive modes depending on the SOC of the supercapacitor. The CSS also assists the manufacturers in product development by providing them access to the data. And finally, the system also maintains the temperature of the supercapacitors at the optimal temperature for best output and efficiency. Now we will discuss the functional requirements of our system. The most important functional requirements are the following. CSS shall permit the user on infotainment panel to register using his user ID, email, and password, and create his account on cloud to access data. Central Software System shall provide an option on the infotainment panel for the user to delete his account so that a new user of the vehicle can register his email as the new user ID. Central Software System shall enable the cooling system whenever the temperature rises above the 50 degrees Celsius threshold. Whenever a vehicle manufacturer rolls a vehicle out of its plant, a database table specific to the vehicle will be created on the cloud storage with a unique ID. This database will be a placeholder to store day and time-wise values of SOC and temperature. Subsequently, when the user will purchase the vehicle and post-purchase register his ID, the same user ID will be tagged to respective database table as mentioned in functional requirements pertaining to user registration. Central Software System shall calculate the value of SOC based on the relationship between localized surface plasmon sensors, intensity, and change in wavelength, and will also calculate the value of temperature. Monitoring shall take place at every millisecond interval. Central Software System shall store the value of SOC and temperature on the internal storage of the vehicle and also on the cloud. The vehicle user shall be able to view the SOC and temperature values in graphical format on the infotainment panel. Central Software System shall enable by default the following driving modes based on the value of SOC and display it on the infotainment panel screen. If the SOC is above 70%, then all the three driving modes are enabled. If the SOC is between 30 and 70%, then only eco and auto driving modes are enabled. And if the SOC value is below 30%, then only the eco driving mode will be enabled. Now let's move on to the non-functional requirements of our system. We have categorized our non-functional system into 9 categories as below. All responses will be carried out within 2 seconds of initialization. The CSS screen can be accessed from both the infotainment and also the desktop of the manufacturer. The CSS shall be secure enough so as not to compromise on the performance of the vehicle or its controls or the database at the back end. The CSS shall enable roles and privileges-based authentication and access mechanism. Data stored on the internal and cloud storage shall be only in view mode for vehicle manufacturer and the vehicle user so that the data cannot be tampered. The CSS shall be available 24/7 and 365. The CSS shall meet the following key performance indicators. Mean time between failures should be greater than 1 year, and mean time to repair should be less than or equal to 2 hours. Our next stop is the task model of our system. First of all, we build the system environment and get the database ready in a cloud environment. Then we implement the functionalities in the order as given below, starting with vehicle details, population, and ending with backup and recovery functionality. Thank you.
Now let's talk about system architecture and the blueprint of our software system. Let's talk about the major components of Kappa cars. There's an industry database, which stores the sensors log and the cooling status. There's also a vehicle system, which is communicating between vehicle control system, UI application, and the hardware components. There's also a control system, which is integrating via UI application to the vehicles. And of course, there's a driver, which is performing infotainment-related tasks. Now, let's have a look at the three-tier architectural pattern. We have vehicle type, vehicle drivers, which is connected to the presentation layer. In the presentation layer, there's a view rendering, especially the SOC and temperature view, drive mode selection interface, as well as the cooling status view. There is also the application layer, aka the business layer. There's sensors which activate driving mode selection, as well as a vehicle system which updates the cooling status. There is also data layer, which there are sensors log and the cooling status connected to the internal data storage. There is also driving mode selection data, which is connected to system admin service. And at the end, there's a vehicle component database, in which the system admin service is connected to the cloud database storage.
We now move on to the class diagram and descriptions. We have used the MVC or the Model View Controller design pattern to classify the classes. We have a total of 6 superclasses falling under the model classification. Of these, the user class is majorly concerned with defining the functionalities provided to the user, like logging in and viewing the vehicle engine's charge and temperature, which are hereby termed as the performance stats. The vehicle system class is mainly concerned with acquiring and updating the charge and temperature values from the sensors, while the vehicle manufacturer class is concerned with storing certain specifications about the vehicle, like its chassis number and make model number. Lastly, we have 3 classes: cloud storage, internal data storage, and system admin, all managing the storage and updation of information in different locations. Next, in the controller subclassification, we have 3 classes under the superclass infotainment controller: SOC and temperature controller, display controller, and mode state controller, all concerned with communicating changes in the model classes related to drive modes, account information, and temperature and SOC with the respective view classes and updating the view classes. Another class, the external controller class, does the same for the defined external environments, that is, any non-infotainment display environment, and particularly so for our stakeholders like the vehicle manufacturers. Lastly, we have 2 superclasses in the view classification: the infotainment panel and external view classes, concerned with displaying the details on the infotainment screen, which is our local environment, and the external environment respectively. A detailed class diagram has been included in the next slide, so I would suggest pausing the video to take a good look.
Now we move on to the user interface design and discuss more about some UI principles of Kappa Car software system. For more details, just pause the video and see descriptions. Now, regarding the first page, our user will see the infotainment setup, in which there will be exact name of the model, and there will be continue button to register or log in the existing account. For the existing account, there will be name, email, and password. If password is lost, we can recover using Facebook, Twitter, or Google. Otherwise, we create a new account, and by clicking this, we will have a new page wherein some additional information will be revealed, such as model name, engine name, and chassis name. Now, when all the setup is finished, our Kappa cars will organize such a beautiful screen panel with 4 important aspects. Now, the first and one of the important one is the SOC, as known as state of charge. State of charge will reveal the percentage and how much distance is traveled. Moreover, we can see the whole diagram of how much state of charge has been fluctuated over the week period. And if there are some boundaries that we should provide, we just press the button called set limit. Now, regarding the drive mode, user can easily choose this button in order to see which option car gives us to see which eco mode or sport mode is better to use for fuel efficiency storage. Our supercapacitor measures this using the threshold values. And since user will have to choose which one is best, there will be options to review, and there will be diagrams to analyze which one of them would be much suitable for such circumstance. Moreover, in every circumstance, there will be a map revealing where the car is located. Now, when we move to the vehicle manufacturer manual, we know that they can easily track the SOC values, as well as range and temperature. So we provide such a mobile applications where they can easily use our supercapacitors, as well as Kappa cars, to see what's the cooling status and what's the SOC. And for the cooling status, we have such a beautiful design pattern. When we go back to the desktop application for the system admins, we will also provide a computer-based UI design, wherein the system admin can choose which driver is best suitable for his choice or for her choice, as well as see the required SoC values, drive modes, ranges, and cooling status. For instance, if user chooses a cooling status, the user will see the CyberTark tester model with the temperatures, with the SoC, and with the desired ranges, basically.
Now myself, Ainesh, is going to cover refined use cases and sequence diagram. This slide captures the summary of total 16 use cases for our CSS system. The use cases which have been refined are marked with an arrow against them. This slide captures the key use cases which have been highlighted in yellow. The use cases highlighted in light blue color indicate the usage of include scenarios. This slide also captures the refinement done in use cases. For example, internal storage is removed as an actor. Use cases are redefined to indicate the verb action. One of the extend scenarios is converted to include condition, and one of the scenario is expanded to include recovery as well. Now this slide captures the refinements done in use case description, for example, enhanced preconditions, main flow, and extensions. Also, the description for all key 6 use cases have been refined. Now I will cover refinements done in sequence diagrams. This slide captures the summary of key sequence diagrams and details of refinements done. For example, reference to various classes defined as part of MVC design pattern, expanded scenario diagrams to detail out the sequences and mention the various methods used in sequences. I have also given a detailed explanation for each sequence diagram. Now this slide captures the example of refinement done in one of the sequence diagram. Here I have also highlighted the mapping of class to MVC pattern and also given one example of the detailed explanation. Feel free to go through the explanation. Thank you everyone for your kind attention.